As a quick starter, and hopefully this is one you should be able to do quite easily, can you draw a quick equation for the formation of butanene, and if you draw the repeating unit that it makes, that keeps you up to date. So butanene, not butene. Have a go, if you want to, have a go with butene as well, nice little extension. And also have a think about how beer or wine is made. Something that's quite important to lots of people's hearts. Beer or wine, I say important for people's hearts, I mean close to people's hearts. So, we're going to be talking about the properties of alcohols today, and if you go to your textbook, it is pages 216 to 219. And we're going to be talking about how to classify alcohols into primary, secondary, and tertiary. Very similar to the work that you did with carbocations when we were looking at alkenes. We're also going to talk about hydrogen bonding in alcohols, because that actually really helps us understand why they're soluble in water, why they're actually relatively non-volatile compared to some compounds with the same molecular formulae, and we'll just have a look at the properties of them. So, first thing is, what is volatility? And the volatility is the ease with which a liquid will go into the vapor phase. So, for example, if I have some ether, and ether was a solvent, or it is a solvent that's used quite commonly, it has the same equation as butanol, because it's got, let's see if actually my drawing pad will work. I've got to say, this is probably going to be terrible, but we can sort of see if I can get it to work. This is a new thing for me as well, so change the pointer and we can see this. Oh, this is really difficult. This would be diethyl ether, and of course we've got this, which would be 1, 2, 3, 4. This would be butan 2-ol or butan 1-ol, doesn't quite matter. This one here has a really low boiling point. It's also very volatile. If you just leave it in a beaker, it will be gone very quickly. It just goes into the vapor phase really easily. And that is going to be because of the lack of hydrogen bonding. We'll discuss that a little bit more later. So, the first thing is this quiz. Have a quick look and see what you already know. You would have done quite a lot of this work at GCSE. You would have, if you've done the AQA triple, then you would have done a unit on organic, and you would have had some big inputs with alcohols. Also, if we have a look here, this one here, you should be able to name this, and you should be able to name any of these because you've done your module on naming. So what I'll do is, if you want to pause this, have a look. We will go through the answers a bit later towards the end of the lesson. So, we're talking at the moment about alcohols, but there are alcohols that are aliphatic, but there are also alcohols that are aromatic. And please remember the word aliphatic, really important word. It means they're straight chains, branch chains, or cyclic, but they are not aromatic. Okay, so aromatic means they have a benzene ring in them. So aliphatic things are things without a benzene ring. What is the general formula of an alcohol? It is based on the alkane formula, and if we look here, it's CnH2n plus 1 OH. Or we could also say CnH2n plus 2 O. But we put the functional group over on the side of this to help. Just to remind you, this does not work if there are rings on the alcohol, because if you form a ring, you have to take up 2 hydrogens, and you take those off and allow the ring to bond together, because carbon can only have 4 bonds going to it. So, aromatic, as I said earlier, this means that you have a benzene ring. and we'll be talking more about benzene rings in the second year or later this year, depending on how the plans go for how we're proceeding. So this is an example of an aromatic alcohol. The one over here, which I'm circling now, this is phenol, and this would be methylphenol. And then this would be an alcohol where the OH group is actually not on the aromatic ring, but it is an aromatic compound because it's got this benzene ring on it. This aromatic compound would be called phenol rather than any other name, and this would be methylphenol. So really important that we know that they're different. Again, we will talk more about the phenols later this year or next year. So how do we name alcohols? It is the same as you've already been doing. You find the longest chain that contains a carbon attached to an OH, because the OH is the important part if it's just an OH group, and you give the OH group the lowest number. Really important, it's the lowest number. The only exception to this is if you have an alcohol and a carboxylic acid group on the same molecule, in which case the carboxylic acid takes priority. Just when we're talking about priorities, you can see on the board here that there is a sort of like an order of priority that you can do there. So point number 3, have a read of that. It is quite sort of obvious. It's just sort of alkyl group, alkene, alkyne, alcohol, ketone or aldehyde, and then carboxylic acid. So it's, excuse me, coffee. It's really important that you understand this order and just sort of learn it if you can. So with anything that is where the alcohol is most important, so we're not talking about ketones, aldehydes or carboxylic acids, you name the alcohol and the end of the word is -ol. So that makes us the alcohol. If you have a higher priority group present, so for example, if you have a carboxylic acid group and you've got an OH group on the other end, it is hydroxy. So the OH is called hydroxy. Think about the hydroxide ion or the hydroxy radical. That is how you name it. And of course, if there's more than one of the OH groups present, make sure you use di, tri, tetra, etc. Okay? So, let's have a look at some names of alcohols. Firstly, we're going to have a look at the names, but secondly, what we want to do is to see what type of formula is shown. So this type of formula doesn't have any sort of branches, it's not a displayed formula. This, of course, is propan-2-ol, and what type of formula is it? Well, this one would be a structural formula. We have butane 1,2,3-triol because we have 4 carbons, 1, 2, 3, 4. Although this is probably not the way I'd normally draw it. I would personally draw it more like this: 1, 2, 3, 4, and then just do the OH, OH, OH. Oh goodness, I'm going to try. Oh, it's all gone wrong. I have no idea why it just disappeared. It's probably just as well it disappeared because I am terrible at using this graphics tablet. I will learn at some point. You will notice my skills will develop as we do these videos. This is, of course, a skeletal formula, and this last one is a displayed formula. Oh, that's so embarrassing. So, how do we classify alcohols? So, if we have a primary alcohol, we've got to think of it in the same way as our carbocations. So, a carbocation, a primary carbocation, had 2 hydrogens attached to it. And it's exactly the same with alcohols. We can see we have an R group, and this is just more CH2, CH3 going downwards. But the carbon that the OH group is attached to has 2 hydrogens attached to it. So this means it is a primary alcohol. Secondary alcohols are going to look more like this. We have a carbon, it has one hydrogen attached to it. It has two R groups, and that could be two different R groups or two of the same R group, it doesn't matter. And we have an OH group. So because we have one hydrogen, this is now a secondary alcohol. And these are examples of secondary alcohols. We can see this one here, which is propan-2-ol. This is 1, 2, 3, 4, 5. This is pentan-2-ol. And remember, this is the most important because we keep the numbers as low as possible. So this would be 1, 2, 3, 4, 5, pentan-2-ol. Tertiary. So have a think about it. With the primary, we had two hydrogens. With the secondary, we had one hydrogen. What do you think we're going to have with tertiary? You would be absolutely right if you said no hydrogens, because we've gone from 2 to 1 to 0. So we've got no hydrogens on a tertiary alcohol. And as we can see, we've just got the OH on the carbon and 3 different R groups. So these are examples of tertiary alcohols. So this would be 2-methyl-propan-2-ol. This one would be 1, 2, 3, 4, 5. So it's going to be based on pentan, and the lowest number is 2. So it's going to be pentan-2-ol. And we can see we've got 2-methyl-pentan-2-ol because this is 1, this is 2. Oh, it gets worse. I'm so sorry. It's much better than it used to be, though. It's terrible. Anyway, so that's it. Just also remember that this can go around the corner. So if there were a longer chain on here, so if this was an ethyl group, it would actually be hexan-3-ol. And it would be 3-methyl-hexan-3-ol. But it's not. So let's have a quick look and see what classification these alcohols have. So this one here, you can see how many hydrogens does this carbon have. It has no hydrogens attached to it. So I would say that this is going to be tertiary. Let's have a look at this one here. We have 1, 2, 3, 4, 5 carbons, so it's definitely pentan something. We can see the carbon has one hydrogen attached to it, so therefore it must be secondary. This is pentan-2-ol. Let's have a look at this third one. We can see the carbon has 2 hydrogens attached to it, so therefore it must be primary. And this is prop-2-enol, or in-1-ol. My goodness, that is a bit of a mouthful. Don't try saying that when you've had any of the ethanol. So, what kind of bonding forces are there in alcohols? There are, of course, 2 different types of bonding force. They are intermolecular forces, and intermolecular forces are forces between molecules, and we have intramolecular forces. The intramolecular forces in alcohols are going to be covalent bonds. So intramolecular means in between or in the actual molecules. So this would be an example of an intramolecular force, a covalent bond. Of course, we know a covalent, oh my goodness, I have no idea what I've just done. And of course, we know that a covalent bond is made from 2 electrons. The intermolecular forces, and this is the forces between molecules, so this would be the force between 2 different alcohol molecules, are firstly London forces, so London dispersion forces exist everywhere. There is a permanent dipole-dipole interaction, because if we look at this, oh, I really don't want to see what happens here. Oh, that's not too bad. We've got a delta negative, and we've got a delta positive here. So delta negative oxygen, because oxygen has lots of electrons and it wants to pull more electrons towards it because it's very electronegative. we have the delta positive carbon because it is more positive than that OH group. So there is a permanent dipole-dipole interaction. If you think about it, if you have two alcohols right next to each other, they can interact with each other because there's this permanent dipole. And because we've got an oxygen, something highly electronegative, and a hydrogen bonded to it, we can get hydrogen bonding. And hydrogen bonding are dative bonds between oxygens, or our electronegative atoms, and hydrogens. So let's have a quick look at the physical properties of alcohols, and we'll sort of think about why they are what they are. So it makes no surprise that methanol, the simplest alcohol, has a low boiling point, 65 degrees centigrade. It's not particularly high boiling point, so actually that's pretty good. And as you get bigger, molecule-wise, the boiling point goes up slightly. And if we think about it, this is going to be due to the increase in London dispersion forces because there are more electrons around, so therefore molecules can be more sticky, if you will. They will have greater forces required to separate them. That's what we're doing when we're boiling things. We're adding some energy in the form of heat to separate the molecules. So propan-1-ol, we can see that actually propan-1-ol has a higher boiling point again, but if we go to propan-2-ol, actually we have a slightly lower boiling point. Why do we think that is? They've got the same molecular formula, they've even got the same functional groups, but why do we think that actually making it from primary to secondary, why does that reduce the boiling point? If you're thinking about London forces, London dispersion forces, and the fact that if I have something like this, oh, that was not good. We'll leave that there. If I have something like this, getting better, and something like this, if we have a branched chain, they cannot get as close to each other to exert London forces with each other. We do still have some hydrogen bonding in there, but actually if they are that close to each other, or sorry, if we have two of those stacked up, they can't get as close, so they can't exert London dispersion forces on each other. If we have a look at butanol, so butan-1-ol here, we see the same trend. As we add a carbon, we are increasing in boiling point because of the London forces, but then if we move over to the secondary alcohol, the chains can't get as close together, which means that the London dispersion forces are more, they are lower. If we go to a tertiary alcohol, and we can have a look at this nice simple tertiary alcohol, we get this effect made even bigger. And if we think about it, this is what the molecule will look like. Probably not, because I'm terrible at drawing with this thing. Oh. Vaguely looks like it. We can see that actually two molecules of this sat side by side, it would be very, very difficult for them to get close to each other. Oh my goodness, I think I need to delete those horrible drawings. That is terrible. By the way, I am just using the smallest graphics tablet ever. I think I probably need to get a better one and get better handwriting. Then again, it's no worse than my handwriting on the board. So, if we look at an alkane and an alcohol, if I had a look at ethane, for example, ethane has a very, very low boiling point. I don't know exactly what it is, but it's probably around -50, for example. Whereas ethanol has a boiling point of 78 degrees centigrade. Why is this? The reason is hydrogen bonding. And because of the hydrogen bonding, it takes more energy to separate molecules, and this is due to the permanent dipole moment which exists over here. We've got delta negative here on the oxygens, delta positive on the hydrogens, delta negative on the oxygen here, delta positive on the hydrogen. In fact, a little bit further back, I did also put a delta positive on the CH3. That does still exist because this is the most delta negative, but actually it is correct to put the delta positives on the hydrogen. And we can see that we have an interaction between the hydrogen and the oxygen, and this is called a hydrogen bond. And it's a really, really important bond. So if I look here, we've got propane here, which has about the same formula mass as ethanol. Propane has a boiling point of minus 42 degrees centigrade, and ethanol has a boiling point of plus 78 degrees centigrade. The propane does not have any hydrogen bonding, whereas ethanol does have hydrogen bonding. So it has both London forces and hydrogen bonding, and we can see it makes a massive difference in the boiling point of ethanol. So what about solvent properties of alcohols? I think if you remember when we did our limonene experiment, when we were extracting limonene, we put heptane into the water to help extract the limonene from the water, and it was very, very immiscible with water, which meant it formed two totally separate layers. So we know that alkanes in general do not dissolve in water. Think about oils. Oil always sits on top of water, so low molecular mass alkanes are not soluble in water, whereas low molecular mass alcohols are soluble in water. And the reason for this is the hydrogen bonding. So we have a high degree of hydrogen bonding, and if we look, our alcohol can interact and sort of stick to water molecules. There is a rule in chemistry that's been said many times that actually if molecules look a bit like each other, it's more likely that they will be soluble in each other. So the hydrogen bonding between the alcohol here and the water molecule means that alcohols are more soluble in water. We find, though, as alcohols get bigger and bigger and bigger, longer chains, this effect decreases, so they become less soluble the longer they get. And actually this makes sense, because if you think about it, if I have a large tail here, so large hydrocarbon tail, it's going to look less and less like water, so it's going to be less and less soluble. So because of the hydrogen bonding as well, this is why alcohols are not particularly volatile. They will evaporate, and they'll evaporate quite quickly, but as I said, they'll evaporate a lot more less readily than something like ether, which doesn't have any hydrogen bonding. So let's review that quiz from earlier on. So what is the functional group in an alcohol? I'm hoping that you said the OH group. What's the general formula of alcohols? So methanol, ethanol, propanol, anything that's non-cyclic. Very similar to the alkane one. However, we have an OH on the end and we've taken away one of the hydrogens. Again, it is correct that you could actually write CnH2n plus 2O. But the thing with that is you could mix that between lots and lots of different functional groups. For example, these ethers we were talking about. Why does ethanol have a higher boiling point than ethane? I'm hoping we can answer that easily. Ethane only has weak London forces, whereas ethanol has our London forces, and we also have our hydrogen bonding, which are very, very strong intermolecular forces. Why does pentanol have a higher boiling point than methanol? This is because as chain length increases, we get more surface contact. So this is really, really quite simple. The bigger the molecule, the more electrons they'll have, so therefore they can contact each other a little bit more, and those London forces can increase in their strength. So, named the following. I'm hoping you got this right. So this one here we have, oh there we are, there's my pointer. We have 1, 2, 3, 4, we have 4 carbon atoms in our longest chain. So we have the alcohol at carbon 2, and we also have a methyl group at carbon 2. So this is 2-methyl-butan-2-ol. Oh dear, pressing the reveal revealed all of them. Have a quick look and mark off what you think. So this one's 3,5-dimethyl hexan 1-ol. If we remember, because the OH group is the most important thing on this molecule, that is where we start. So that's going to be our lowest number, and then we have 1, 2, 3, 4, 5, 6. So it's hexan, and then we've got 3,5-dimethyl. So this is carbon 1, 2, 3. It's got a methyl. 5. It's got a methyl. Let's have a quick look at this one here. So we have 6-methyl, 3-heptanol. So we've got 1, 2, 3, 4, 5, 6, 7. So it's the heptanol. This is on carbon 3, so it's 3-heptanol. And then on carbon 6, we've got methyl groups. Let's have a look at these bottom ones. So we have cyclopentane here. And if it's going to be, this is the most important thing, so it's going to be cyclopentanol. And we're looking at 2-bromo, 4-chlorocyclopentanol. We have 1,2-ethane diol. This is ethylene diol, glycol. This is actually in antifreeze and stuff. It's actually a very toxic chemical, but actually we do come across it quite a lot. When you spray your windscreen with the windscreen solution, that is what you use. This is propane, 1,2,3 propane triol, or glycerol. Very, very important biological molecule. Your fats are esters of this alcohol, so this is actually a really important molecule. Also very useful in soap, and those antibacterial hand gels that you've been using, they use it to stop your hands dehydrating when you put that sort of alcohol solution on your fingers. So it's quite an interesting sort of idea. So these are your tasks. Have a quick read of page 216, 219. Answer questions 1, 2, 3, 4 and 5, and you go through your booklet and see if you can name and classify those alcohols. So that's enough from me. I'll get this onto YouTube and I'll speak to you soon. Let's see if I can turn this off now. Bye bye.